Today I want to talk about white dwarf crystallization and what it has to do with the age of our galaxy. We got a lot to cover here in only 10 minutes, so let's get into it. So this is Russell and Hertzsprung, and they were a couple astronomers from the early 1900s. And what they noticed in their data, what they each noticed independently, was that stars tended to follow along a continuum, where they went from bright and blue down to darker and red. And this is kind of a diagram of their observations. So right here in the diagram is where our sun would be, and as it ages, it'll move up this branch and become a red giant. And when it runs out of fuel for fusion, it'll kind of explode and it'll become a white dwarf. And you'll notice that the white dwarfs also kind of follow the same pattern. They go from bright and blue down to dark and red. The European Space Agency put this probe up in 2013. It's called the Gaia probe, and it basically has been mapping the stars in our galaxy continuously ever since it went up. And it collects data on their location, their brightness, and their color. So based on Gaia's data, this is the Hertzsprung-Russell diagram for the stars in our galaxy. And you can see the giant branch over here. Here's where our sun would be, and we go down to red dwarfs. And then down in this corner, we have the white dwarfs. And I want to zoom in on this little part in the white dwarf diagram that's called the Q branch. And what you can see there is a bunch of dots. There's just more white dwarfs that fall in this area where they're bluer than would be expected for how bright they are. Now, I mentioned white dwarfs, they don't have any nuclear fusion going on, so they don't produce any heat. So what you would expect is that they would start out bright and blue and go down toward dark and red. But we have a little group that just isn't quite following that pattern, so what gives? This is kind of a reference for the next diagram I'll use. So what this describes is three different classes of white dwarfs. You got this one that is the lightest carbon and oxygen core, a thin layer of helium covered with a thin layer of hydrogen. You got this next one that again is carbon and oxygen, a little bit heavier, and only has the helium atmosphere. And then you got the heaviest ones that primarily consist of sodium, magnesium, neon, and then they have a carbon and oxygen atmosphere. And this little one is kind of important because that hydrogen produces a very, very predictable spectrum as the white dwarf ages. And based on looking at how those white dwarfs cool as they age, and this is with data prior to what was being accumulated by Gaia, the age of the galaxy was estimated to be 11.5 billion years. And it was just based on what is the color pattern and the brightness of the oldest white dwarfs we see. Well, a couple problems have come up caused basically by that Gaia data. As I mentioned, it keeps going around and it keeps looking again and again at stars in our Milky Way. And in this study, what these two researchers looked at were stars near the core of the Milky Way. So this little chunk here of our galaxy, the innermost part, is the part that would have formed first. So there basically was an initial halo of dark matter that pulled in hydrogen and helium gas. So the initial stars that form in there should just be composed of hydrogen and helium. And then over time, as stars form, blow up, and collapse, there would be more and more other elements that show up. And what those researchers specifically looked at is how old are stars and how much iron is in them. So the older a star is, the less iron it should have in it relative to the amount of hydrogen it has. Well, on this graph, the age of the star is on the bottom line here. So the oldest stars they're finding were much older than 11.5 billion years. And then you have a chunk that have a whole lot of iron in them that are showing up before 11.5 billion years, which really doesn't make any sense. It would mean that the core of our galaxy was fully formed way before 11.5 billion years. So based on their data, they put the formation of the Milky Way at around 13.2 billion years. And since the whole universe is only around 13.8 billion, it means the Milky Way is almost as old as the universe itself. So you have this conflict between how old the white dwarf cooling says our galaxy can be and how old it has to be based on the composition of the stars near the core. Well, there was another chunk of data, this time on white dwarfs from that Gaia probe, that made the mystery even a little bit deeper. Because of how white dwarfs are composed, they're basically, all the atoms in them are crunched up together. So as you add mass to a white dwarf, it actually shrinks. And eventually it shrinks down enough to cause the electrons in the atoms that make it up to collapse into the protons in their nuclei. And that basically causes the white dwarf to explode. So there's a limit on how heavy a white dwarf can get. And it's estimated to be close to 1.5 times the size of our sun. And this is the measured data for the population of white dwarfs that are visible from Earth and how heavy they are. And you can see most of them are in that half the weight of the sun to around 0.75. And there are only a few that are the same weight as our sun or heavier. Well, because white dwarfs are lighter than the stars around them, they get flung around like a rock in a sling. So this graph once again looks at that Q branch, and it's kind of complicated. They've got brightness on this left-hand side, and then at the bottom, there's once again red going toward blue. And then they added this additional piece of data. So we've got blue on this side, which represents the speed a white dwarf is moving at. So blue on this side is slower, and magenta is faster. So as a white dwarf ages, it should get flung around more and more. So the oldest white dwarfs should be moving fastest. So less bright, more red, and moving faster. But we've got all these white dwarfs in that Q branch, in that anomalous Q branch, they're both bluer than you would expect them to be, and they're moving faster than you would expect them to move. So less bright indicates that they're older, moving faster indicates that they're older, but their color indicates that they're younger. And because that color is associated with heat, it means they're hotter than they should be for their age. Another thing to note is that this group of white dwarfs is heavier than most. It's within that 1 to 1.25 solar mass range. And if you remember, as I pointed out, the vast majority of white dwarfs are in the 1/2 to 0.75 solar mass range. Well, these researchers came up with a model that may explain the discrepancy. So here's what they came up with. What if you had two stars that were near the end of their life and they happened to merge? Then you would get something that had a core that had a lot of heavier elements like this, but would still have enough hydrogen to create a hydrogen atmosphere. But then, since you'd have this mix of heavier elements within the core, they would start to crystallize, and the heavier crystals would start to fall to the bottom. And that would mean the lighter ones would have to move to the top. And then just like you have a lot of energy released when you drop a rock into water, you'd get the same effect when heavier elements went to the bottom of the core. You'd also have the friction as these different elements move past each other. And enough energy would be released to maintain the color of these white dwarfs within the Q branch. So I think this mystery is probably solved.